Welcome to the second video of the 4-video set that comprise the ECOFusion webinar. This video begins the scientific presentation of ECOFusion, which starts with an overview of the completed analysis and does some setting of the initial parameters of the ECOFusion device. The completed analysis and calculations have been quite complex. There are 3 regions of analysis in the ECOFusion system. We have regions where the deuterium and tritium beams are in collision, regions where the deuterium and tritium beams are overlapped by electron beams for cooling, and regions of free transport that transport the beams from the colliding region to the cooling region and from the cooling region to the colliding region. There are many entities in each region. There can be one or more beams, background gas, trapped charged neutralizing particles, walls, and superimposed magnetic fields. The 4 known forces are gravity, electromagnetism, and the strong and weak forces. Fortunately, gravity can be neglected because it is so weak, and the strong and weak forces are wrapped into the fusion cross-section for the analysis. This leaves the electromagnetic forces as the only forces that we need to analyze in detail. The electromagnetic forces break down into scattering and collective behavior categories. The scattering category involves DEDX processes, whereby ions lose their energy to electrons in the medium, single scattering events of tritium off of deuterium when they're in collision, multiple scattering events of deuterium off of tritium when they're in collision, and involve many small angle kicks that build up over time, and intrabeam scattering, where particles within either the deuterium or tritium beams scatter off of other particles in those same beams. The collective effects include beam steering and focusing, which is known as ion optics, space charge effects, resonances as the beams go around the same system many times, and instabilities that can build up within the device. The scattering and collective effects have been analyzed for all of the entities in each region, but only the highlights will be presented in this webinar. For the initial calculations, the first thing of note is that we want to keep the optics the same for both the deuterium and the tritium beams. That way the focusing magnets will focus the beams to the same small spot size at the same place. Because of electron cooling beams single scattering, we're going to set the energy a bit higher than one would have at the peak of the cross-section. We'll set the center of mass energy at 400 kilovolts. At that energy, the fusion cross-section is 0.85 barn. The energy of the tritium beam is 160 keV, and the energy of the deuterium beam is 240 keV. Possible parameters that have been evaluated in detail include an interaction length of 1.2 millimeters, deuterium and tritium currents of 10,000 amperes, and a radius of 90 microns. Those parameters lead to number densities of 5 times 10 to the 17th per cubic centimeter for the deuterium beam and 7.7 times 10 to the 17th per cubic centimeter for the tritium beam, which in turn leads to an output power of about 30 kilowatts per focus region. Here we see a plot again of the interaction cross-section. We've chosen the design point to be at the point where both the deuterium-tritium cross-section and the deuterium-helium-3 cross-sections are about equal. Later, we'll discuss in the summary section how we may have overestimated the effect of the electrons' single scattering problem, and we may be able to work our way up the curve a little bit for further advancements in the future. Given the parameters we've just looked at, it is of interest to calculate some parameters of a 1 gigawatt power plant. Each ECOFusion cell is about 1 meter high by 3 meters wide by 22 meters long, and each ECOFusion cell in the present design produces close to 60 kilowatts of power, since there are 2 interaction regions per cell. Therefore, a 1 gigawatt power plant would be about 220 meters wide by 219 meters long by about 24 meters high, which is similar to coal-fired electrical plants today. Next, we'll begin our analysis by looking at some of the ion beam physics issues within the ECOFusion system. The first issue that we will look at is the presence of the neutralizing self-space charge that's needed. The electron beam will neutralize the ion beam space charge where those two beams overlap, and trapped neutralizing electrons will exist in all other regions. It's important to realize that the electrons will neutralize the core of the ion beam, and a small shell of net positive charge will form that will provide the containing electric field for those electrons. An equilibrium will then exist between the DEDX heating as the beam goes through those electrons and the cooling of those electrons as the hot ones deposit their energy on the walls and hitting them. I've assumed a Maxwellian distribution for the electrons that do the neutralization. It's important also to realize that this outer shell will produce a beam halo in the ion optics. Here we have a picture of the situation. The ion beam, shown by the orange circle, will be going down the beam pipe. Within the ion beam, electrons will be freed from the background gas, and provided that the potential within the beam from the space charge is high enough, those electrons will be trapped in the center portion of the ion beam. The reason that they will go to the center portion is that it's well known that any excess charge in a conductor always flows to the outside due to the self-space charge forces that are present there. Hence, one would expect a small shell of net positive charge that will surround the electron neutralized region. Since you have a Maxwellian velocity distribution, some of the electrons will penetrate outside of the ion beam as well. And the situation that will present itself is that the total charge within the wall will be approximately zero. The reason for that is if you had a net positive charge and an electron, high energy electron hits the wall, the generated secondary electrons will be accelerated back into the beam, and that will provide a cascade which would then lower the charge. On the other hand, if you had a net negative charge in the vacuum region, the electron self-space charge would repel those secondary electrons back into the wall. And hence you've got a rather stable situation that should exist when you've got a net zero space charge within the walls of the vacuum system. The analysis of the situation that we just looked at did a detailed comparison of the DEDX power loss from the beam to the plasma, as well as the wall loss that cools the electron plasma. In that analysis, it was determined that in the interaction region, the equilibrium estimate will be that we'll have about a 5,625 volt potential difference between the center of the beam and the wall that will trap the electrons. The estimate also is that we'll have about a 1,000 eV electron plasma temperature within the ion beam. This, in turn, leads to an estimate of about 750 watts of DEDX loss per interaction region. The amount of non-neutralized ions in that shell that we saw on the previous slide corresponds to about 2 amperes of tritium beam and about 3 amperes of deuterium beam. For the non-interaction regions, the equilibrium estimates are about a 300 volt trap with a 100 eV electron plasma temperature. In the non-interaction regions, the equilibrium estimate is that we'll have about a 15 watt DEDX loss per beam. And in those non-interaction regions, we'll again have a bit of non-neutralized beam that will lead to halo, which will be about 83 milliamps for the tritium case and about 210 milliamps for the deuterium case. Moving on to other aspects of the ion beam physics study, it's important to note that remnant self-field effects have been looked at as well. These fields in the interaction region imply that we need about a 1 micron steering accuracy at the interaction region so that the oncoming beams do not steer each other off into the walls deleteriously. The focal properties of the self-magnetic field are acceptable throughout the system, and the merge region has also been looked at to see if the fields from the beams as they merge adversely affect each other. it has been determined that those effects are acceptable. Single scattering has been looked at, and in this case, it's been assumed that any particles that undergo single scattering at greater than 200 milliradians are lost from the system. This leads to about a 10-barn cross-section for those losses, which is about 12 times the fusion cross-section. Multiple scattering has been looked at, but it was determined to be negligible in comparison to the intrabeam scattering. The intrabeam scattering is the leading cause of momentum heating in the beams. The analysis has shown that the longitudinal growth in the focal region is about delta P over P of 9.8 times 10 to the minus 4th for the tritium case and 4.2 times 10 to the minus 4 for the deuterium case. Injection has been looked at, and it's determined that a 20 milliradian injection angle for the deuterium beam will be cooled in a single turn through the system. For the tritium case, a 33 milliradian injection angle will be cooled by the electron beam in a single turn. As far as instabilities and resonances are concerned, the single turn cooling that's present within ECOFusion implies that there should be no problems here. Instabilities arise because of a longer term effect, and resonances arise through many turns throughout the system. Since the electron cooling is so strong to cool away these problems, we should not have any problems with instabilities or resonances in the ECOFusion device. Recombination and charge exchange have also been looked at, and those effects are quite small. The equilibrium ion beam emittances have been calculated for both the non-magnetized electron cooling case and the magnetized electron cooling case. In each case, the equilibrium occurs between the electron cooling forces that tend to lower the emittance versus the various scattering effects that tend to increase the emittance. The optics studies of the ion beam use equilibrium emittances that are within the range of the non-magnetized and magnetized electron cooling studies. At this point, it makes some sense to try to do a sanity check about the ECOFusion design and compare it to a known functioning accelerator. In this case, we're going to compare ECOFusion to known existing free electron laser operations. Million electron volt kiloamp electron beams have been produced for free electron laser experiments. The electrons are going to be much more susceptible to instability than are the ions within the ECOFusion system due to the fact that the electrons have a much lighter mass than the ions used in ECOFusion. The ECOFusion device is proposed to use 10 kiloamp, 200 kilovolt ion beams, and the momentum rigidity is about twice what it is for the free electron laser beams. The path traveled by the ions in ECOFusion is shorter than the path traveled by the electron beams, and the particle beam currents are similar. Hence, there should be no instability problems in the short path that the ions are required to traverse in the ECOFusion cell. The important thing to note here is that the instabilities should only occur within ECOFusion over the short path that they undergo prior to or just after going through the electron cooling region. Next, we'll start to take a look at the ion beam optics. We'll cover the SCAT ion optics code, look at the core optics with various design currents, then take a look at halo optics, aberrations, and do a sanity check of the beam optics. Lastly, we'll do a redundancy check against a second ion optics code, Trace 3D. The SCAT ion optics code stands for Space Charge Acceleration and Twists, which was a numerical integration of the beam twist parameters within the presence of space charge, acceleration, and emittance effects. It was first written for the design of an ampere intensity 3 million volt electron accelerator for the electron cooling of antiprotons, which was my thesis work done in 1984. That device worked according to the designs prepared by the SCAT code. SCAT has been used around the world in the UCF free electron lasers, an Israeli electron cooling experiment, Japanese proton therapy design, Fermilab's PET experiment, as well as the ECOFusion device. The core ion optics studies of ECOFusion have been done with the deuterium beam studied at zero current, full current, and half current, and the tritium beam studied at zero current and full current. All current states are possible with magnetic field adjustments, and the magnetic changes were continuous and smooth. What this means is that the beam can be tuned while one ramps up from zero current to full current without having any significant difficulties. This slide shows the deuterium core optics for the ECOFusion system. The analysis shown here shows the deuterium optics once it leaves one electron cooler up to the point where it enters the next electron cooler. The optics within the electron cooler itself is not very interesting, since the deuterium beam maintains a beam radius of about 30 centimeters throughout the electron cooling region. This plot shows the horizontal beam size, half size in red, and the vertical beam half size as the green trace. As can be seen, when the deuterium beam leaves the first electron cooler, it's focused by a solenoid and then by a quadrupole such that the beam forms a very tight waist in two locations within the interaction region. The beam then symmetrically goes out of the interaction region, is again focused down to a very small spot size, and then comes back up to the full 30 centimeter radius where it then enters the downstream electron cooler. There's also solenoidal focusing within the interaction region itself that is responsible for forming the very tight wastes within the system. The reason for the downstream waste is to handle the halo optics, as we will see later. Here we see the various magnet excitations that are needed for the ECOFusion system under the conditions of full current, half current, and no current for the deuterium beam, and full current and no current for the tritium beam. I have not shown the tritium ion optics as well here because this trace is extremely similar due to the identical momentum of the deuterium and tritium beams within the ECOFusion system. The important thing to note about all of the numbers given here for the various excitations of the magnets that are needed is that all of these fields are readily obtainable with magnet technology available today. The halo optics has also been studied in detail. Recall that the halo is produced both in the interaction region and in the non-interaction regions for both the deuterium and tritium beams. Also recall that the magnitude of the halo is determined by the dEdx power loss of the beam going through the electron plasma, which heats the electron plasma, versus the particle loss equilibrium, which takes power out of the plasma as the electrons are deposited upon the wall. This interaction, when it comes to equilibrium, determines the potential difference between the center of the beam and the wall, which causes the trapping of the electrons within the ion beam. It also tells us how much ion current is necessary to create the required fields. The calculation has shown that for the interaction region, currents in the outer shell of the ion beam of 2 amperes for the tritium case and 3 amperes for the deuterium case provide the necessary trap voltage in the interaction region. For the non-interaction region, the currents are 83 milliamps for the tritium beam and 210 milliamps for the deuterium beam. When we look at the halo optics, it's important to note that the halo is only going to be relevant for the beam that's going into the interaction region, as the beam that's leaving the interaction region is going to be immersed in the oncoming beam's halo once it passes the waist. And therefore, the kick that the particles get due to the space charge will only be in force from the maximum beam size down to the waist region. The desire of the optics is to transport all of the halo to the next electron cooler with trajectories that can be cooled so that single turn cooling is desired. The reason you have to do this is if 2 amperes of beam were lost in a continuous way, ECOFusion's power losses would be too large to sustain the desired effect of having more power out of the system than is put in. This figure shows the deuterium halo optics throughout the interaction region for the horizontal portion of the trajectories. The blue trace shows the core deuterium horizontal optics. The green trace shows the halo optics produced by the beam from the first large beam size within the interaction region until the beam gets to the first interaction waist. As expected, the green trace is larger than the blue trace as it goes toward the waist because of the fact that the space charge forces are repulsive. Once it reaches the longitudinal position of the waist, the beam then is immersed in the oncoming tritium beam's halo, and the space charge forces are then turned off in the calculation, and the trajectory is allowed to make its way to the electron cooler. A similar calculation must also be done for the beam that heads toward the second interaction region. That calculation is shown in red. Focusing solenoidal magnets are located at both interaction regions, as well as a quadrupole magnet located at the downstream waist to focus the particle trajectories. By placing these magnets at the waists of the main core beam, the magnets do not significantly affect the core beam optics and predominantly affect the halo optics. In this way, we can focus the halo so that it is of the appropriate size and angle so that it can be contained within the ECOFusion system and cooled in a single turn. Aberrations have also been studied in detail. The chromatic aberrations are introduced by the solenoids. With a momentum spread of 0.07%, it's the chromatic aberrations from the solenoids that leads to the 90 micron spot size used in the ECOFusion design. Spherical aberrations have also been studied, but their contribution is far less than that of the chromatic aberrations, and so the spherical aberrations are not a significant contributor to the beam optics. Dispersion has been analyzed as well. The nominal design is a 40 micron contribution to the beam size, but one could easily reduce this in a future design by making some changes to the focal properties of the system. The system was also studied with Trace 3D, a well-known ion optics code. Trace 3D verified that the SCAT studies were accurate, as was expected. So at this point, it makes sense again to do a sanity check by comparing the ECOFusion design against a known, proven accelerator. In this case, we will compare the ECOFusion design to the design of the helium-3 PET MEBIT accelerator from the recently successful Fermilab experiment. This table presents a comparison between the ECOFusion design and the Fermilab PET experiment. The PET accelerator had a 200 micron minimum beam size. In ECOFusion, we expect to have a 90 micron beam spot size. The maximum angle of convergence in the PET accelerator was 50 milliradians. In ECOFusion, we pushed that a little bit more and designed in a 250 milliradian convergence angle. The maximum beam size in the PET experiment was 4.25 centimeters, and for the ECOFusion design, it's 30. The ion energy in the PET accelerator was 1 MeV and used helium-3 ions. In the ECOFusion design, we use a 160 keV tritium beam and a 240 keV deuterium beam. None of those parameter ranges are significantly different from one accelerator to the other, as each parameter is less than a factor of 10 different from one accelerator to the other. The one big difference between the Fermilab PET accelerator and the ECOFusion design is the current. The PET accelerator had 40 milliamps of pulsed current, whereas the ECOFusion accelerator design calls for 10 kiloamps of beam, and that beam should be continuous. But it is well known that stacking and cooling allows many orders of magnitude increases in currents, and so the sanity check bears out quite well that we expect that the two devices should have similar behaviors in many regards.